Suppose we have a point in the rectangular system denoted P1 with coordinates x1, y1, and z1. Now each time we introduce a small displacement in one of the components of this point while holding the other two components fixed. For example, consider point P1 and let its x-coordinate change by an amount dx. Let us take dx to be positive. However, its y and z coordinates remain unchanged. This gives us a point P2 with coordinates x1 plus dx, y1 and z1. That is, we add dx to x while remaining at y1 and at z1 to arrive at point P2. Now we form the vector P1, P2, we obtain dx times a hat sub x. This is referred to as dl sub x, that is the differential length component along the x direction. Therefore, if a displacement occurs in the rectangular system such that only the x coordinate changes along that line, the magnitude of the displacement equals precisely that change in x, that is dx, in the direction of a hat sub x. We can carry out the same procedure for the y direction. Consider point P3, which is the same as point P1 except that its y coordinate has changed by an amount dy. So we change y1 to y1 plus dy, while keeping x1 fixed and moving the same amount along z1 to obtain this point. Now, if we form the vector from origin point P1 to destination point P3, the coordinates of the endpoint minus those of the starting point gives us dy times a hat sub y, that is dl sub y. Now, consider point P4, which relative to P1 has only its z coordinate changed by an amount dz. If we form the vector P1, P4, we obtain dz times a hat sub z or dl sub z. Now, in the general case, suppose we have a point with coordinates x, y, and z, and another point where the x coordinate changes near the original point, the z coordinate changes by dz. In this case, the magnitude of the displacement is a vector obtained from the coordinates of the endpoint minus those of the starting point, equal to dx times a hat sub x plus dy times a hat sub y plus dz times a hat sub z. This is equal to dl sub x plus dl sub y plus dl sub z. In this way, the general differential length element of the rectangular coordinate system is obtained. Now, what are the standard differential surfaces of the rectangular coordinate system? First, what do we mean by a standard surface? We call it a surface standard with respect to a given coordinate system if on that surface two of the coordinate components vary while one component remains fixed. In that case, that surface is a standard surface of the coordinate system under consideration. Therefore, since in the rectangular coordinate system, we have three components: length, width, and height. That is x, y, and z. The first standard surface is the surface on which x is fixed, meaning that all points on that surface share the same x value while y and z vary. Since we must form a surface, and the surface is formed from the product of length, we must multiply a differential y by a differential z, and on this surface x must remain fixed. Therefore, planes lying on the yz plane or parallel to yz plane corresponding to constant x. This is illustrated here by a very small differential surface element shown here with hatching on which y varies and z also varies by dy and dz respectively. Therefore, our differential surface element is the product of dy and dz, and you can see that all points on this surface have an x-coordinate of 0. However, it does not matter whether that value is 0. What matters is only that it remains fixed. Now, regarding direction, since in flux calculations we need to assign a direction to surfaces, here we take the direction to be perpendicular to the surface. Naturally, if our surface is a standard surface, this perpendicular direction coincides with the direction of that fixed component, either its positive sign or its negative sign or both. Since here we have only a single surface and we have not yet introduced a rule for uniquely specifying the perpendicular vector of a surface, if we consider ds as a vector with a more complete definition including both positive and negative dy dz, then this is written as plus or minus dy dz times a hat sub x, whose magnitude is plus or minus dy dz in the direction along a hat sub x, which is in fact the unit vector perpendicular to the surface. This is denoted ds sub x, defined in the rectangular coordinate system as the surface on which x is fixed. In the same way, we can arrive at the surface on which y is fixed. So here we let dx vary and we multiply it by dz to form a surface on which y remains fixed. Here, for simplicity, y is taken to be 0, though any fixed value of y would be equally acceptable. The perpendicular to this surface is either positive a hat sub y or negative a hat sub y. Therefore, ds sub y is defined as plus or minus dx dz times a hat sub y. And the last standard surface is defined with z fixed. A differential dx and a differential dy are multiplied together to form a surface on which z remains fixed. Here z is taken as 0 for simplicity. The perpendicular to this surface is either positive a hat sub z or negative a hat sub z. Therefore, the vector ds sub z is defined as plus or minus dx dy times a hat sub z. And these three are the standard differentials of the rectangular coordinate system. There may exist a surface that appears rectangular in shape, but when we attempt to write its differential, we find that we cannot hold one component fixed while treating the other two as variable. For example, consider a door hinged along the z-axis, forming some angle with the x-axis. Even though this door is a 1 by 1 rectangle, when we examine it, we see that x, y, and z all vary on it. The points on this door do not lie on the standard surfaces of this coordinate system. Now, the differential volume element. For the differential volume element, we must consider a differential cube. The rectangular coordinate system forms a rectangular box for us if we vary the length, width, and height of the points, and thereby construct a volume at each point. We can obtain a rectangular box. This is precisely why this system is called the rectangular coordinate system. Consider a cube. This edge represents the x and this edge represents the y, which we can see forming the base. If we give that base area a height of dz, our volume is constructed. Therefore, our differential volume element becomes the product of the x, dy, and dz, and in this way the differential volume of the rectangular coordinate system is defined. Now we want to see all these differential length, surface, and volume elements together within this cube. Let us look at our differential length elements here. There are 4 dx segments, which can be represented as dx times a hat sub x, shown here with an assumed positive direction. We also see the positive dy times a hat sub y segment and the dz times a hat sub z segments. Therefore, dl in the rectangular coordinate system is given by dx times a hat sub x plus dy times a hat sub y plus dz times a hat sub z. This is the differential length element of the rectangular system. Now, let us write the differential surface elements. Consider our standard x surfaces. This is the surface that is shown hatched, and there's another surface behind it. So here we have 2 surfaces on which x is fixed. The front surface, whose perpendicular is taken to point outward. Thus, the first rule we introduce it here for uniquely specifying the perpendicular of a surface is this: whenever a surface belongs to a volume, as is the case here, this hatched front surface belongs to our differential cube volume, then in writing the perpendicular of this front surface, we must choose a direction for the perpendicular that points outward from the volume, not inward. That is, if you imagine yourself as a point on that volume, on that surface of the volume actually, when you move in the correct perpendicular direction, you move away from the volume. Therefore, for this front surface, our ds is positive in the positive direction of a hat sub x. However, for the back surface, the direction is negative a hat sub x. If we wish, standing on that surface, to move outward from the volume moving perpendicular to the surface, we must move in the direction of negative a hat sub x for the back surface. Therefore, ds sub x is plus or minus dy dz times a hat sub x, positive for the front, negative for the back. For the surface on which y is fixed, we likewise have two surfaces on this cube. This surface shown here, where dx, dz represents the area of these surfaces. We have two surfaces. The front surface lies in the direction of positive a hat sub y. It's perpendicular. That is, if we wish to move in the perpendicular direction toward the outside of the volume, we must move in the positive y direction. However, the back surface lies in the direction of negative a hat sub y. Therefore, ds sub y equals plus or minus dx dz times a hat sub y. For the surface on which z is fixed, we proceed in the same manner. We have the top surface and the bottom or lower surface. The top surface direction is positive since we must move outward from the volume. The bottom surface naturally is in the direction of negative a hat sub z. In this way, the s sub z for the surface on this cube where z is fixed becomes plus or minus dx dy times a hat sub z. And finally, for the volume, direction is no longer considered. We simply need to multiply the three differential length elements, namely the x, the y, and the z together. The differential volume of the rectangular coordinate system equals dx dy dz.